The first is neutral network-based approach to find solutions to diffusion equations. Mr. Sampath Venkat Sai Rout, Vellore Institute of Technology.
Good morning, sir. Is my presentation visible? All right. So, greetings to the ICIML panelists. Just give me 1 second. I would like to, yes. All right. So, my name is Sampath Ratu, and I'm an undergrad student from VIT Vellore. My paper is called A Neural Network-Based Approach to Find Solutions to Diffusion Equations. So, the contents of my presentation are divided as follows. We'll go through each section individually. So it's basically boiling down the paper into some important facts that I've taken out of the paper. So firstly, the introduction. So let me first try to give a brief introduction to the diffusion equations part. Diffusion equation is a type of differential equation which is very prevalent in physics, fields like physics and finance. One example that I would like to give in physics is modeling the heat flow in a one-dimensional or two-dimensional object. And in finance, the application I would like to give is the Black-Scholes model. It is used to price options. So yeah, so this is how partial differential equations are used. And for the sake of the research paper that I've made, we've only used one-dimensional heat equation of the diffusion, which is in the form of diffusion equation. So that is very much prevalent in the field of physics. And now there are usually when it comes to solving partial differential equations, there are traditionally there are two solutions. There are two ways to solve it. The first one is the analytical solution. Analytical solution is basically getting the exact solution to a specific PDE. When I say solution to a PDE, I mean converting the PDE into an ordinary differential equation and then solving it. So that is one solution. And then the other solution would be to approximate the solution. This is also called using applied numerical methods. There are different methods to do this, using finite difference methods, using Galerkin models, using finite element methods. There are different methods to do this. For the sake of this research, I have used a finite difference method called forward Euler method. And basically, the only difference between them is the time and the computational power consumption of each algorithm. For example, the analytical solution is very hard to at least code it and to get an exact solution. But if we use numerical methods, it is very iterative and a very small change on each level, but then the number of iterations will change. That is pretty much the two traditional approaches to solving, I would say solving, but then to approximate partial differential equations. But the question of interest, or the question that I'm trying to find in this paper is regarding using neural networks and their efficiency to outperform traditional algorithms. Now, in the literature survey, although we have gone through various papers, the most notable ones, I have boiled it down to two slides. And the most notable ones are the papers by Tobias and Lagarius. And they extensively talk about the stochastic optimization problem, which the problem with using stochastic optimization algorithms, especially when given the higher dimensionality of the neural networks, the solutions, the initial based on the sensitivity of the initial guesses, the local minnow gets stuck. And since we're using stochastic optimization algorithm, since we place random solutions first, there'll be a very high bias on the initial guess. So that is one problem, which is not only prevalent in this specific problem, but then in any higher dimensionality neural network problem, that is a very important issue to go through. And another one important feature that has been mentioned in Tobias's paper is the use of SOTA neural networks to solve partial differential equations. Although there has been one innovation which is called physics-informed neural net, that with the exception of that, Tobias's paper mentions to not use the other SOTA neural network architectures to solve differential equations, because the procedure followed in the analytical solution must be designed in such a way that it follows the same analytical solution. So that is one thing. And then finally, the other paper, which talks about the computational cost. And while training networks like this, we have to train equation by equation, and that'll have a very high computational cost if we have the number of iterations high. So that is one thing that I wanted to mention with this literature survey. And apart from that, the experiment design. So initially, putting the analytical solution aside, let me just get the so putting the analytical solution aside, the equation has been formed using this. The number of time steps are 10, the number of space steps, the number of space steps are 100, and then this is the exact specification for the neural network, and this is basically how the neural network is constructed. And the data used has been given down by my numerical methods professor for different various heat modeling problems with the parameters of x and t, where u will be approximated. Now, I would like to go through the since it's graphs and numbers, I would like to go. These are very intuitive. I would like to just go over them very quickly. When we ran the experiment, when we used the test experiments, so first, I would like to show you the results gotten by the neural network approach. As you can see, the mean square error that we've gotten are almost in the order of 10 power minus 2 to 10 power minus 3, whereas the results gotten by numerical methods are one set of them are on the order 10 power minus 6, and then the other ones all almost in the 10 power minus 3 to 10 power minus 4 range. So one interesting finding that we found from this is as we have more fine tune, like when we have more intervals in the x space, we can see the mean square error gets considerably small, whereas we can see that even it doesn't matter how small or how big the spaces are, the mean square error remains consistent throughout all of the iterations. And by conclusion, what we can say, as we've gone through the neural networks and its performances, it is definitely plausible to use neural networks to solve differential equations. But the training period is definitely higher than that of numerical methods, and it is also yielding a higher MSE, higher mean square error compared to the forward Euler approach. So I would say the future work would definitely remain to investigate on how physics-informed neural networks are used, because these physics-informed neural networks are specifically designed to follow the analytical solution part of it. So that is my presentation. Thank you.
Just do and let me know whatever work you have done.
Sir, yeah. Like, should I go through the presentation again, sir?
No, to the presentation. What I'm asking, whatever work you have done, have you compared with the latest work?
Yes, sir. From the literature survey, those are the latest papers in the field which have used like basic neural networks to compute to approximate the partial differential equations.
Okay. Can you tell me which is the base paper of this particular work?
The base paper would definitely be Tobias's paper, sir. Just give me. Can I give you the link to that or something?
Yes.
Can I drop it off in the chat?
Yes. And what is the difference between that particular work and your work?
So the particular work that they have worked on is basically to check what. So they haven't actually used this exact diffusion equation only, sir. So what they have done is basically to see a general approach of how neural networks work. So, and they've only seen how it works with the analytical solution. So basically, what I've done is basically saw a comparative analysis of numerical methods as well as neural networks, sir.
Okay.